Today I'm going to do a quick video on how to write a double replacement reaction for a precipitation reaction and how to write the net ionic equation. So you might see an example like the one on the screen. You have two ionic compounds reacting in solution. And all you do is you are going to essentially switch the two positive ions. So those two positive ions should now be with different partners or replaced with different negative ions, and that's why it's called a double replacement. So for instance, in this case, the two positive ions, the Pb2 plus and the K plus, are going to switch places. So where the Pb once was, there's going to be a K, and where the K once was, there's going to be a Pb. Now, when you switch these partners and they are combined with new partners, subscripts are going to change up. So somewhere on the side of your screen, you've got to look up the charges, switch them, and make them subscripts to find the formulas of your new products. So for instance, the K was with the Cl, now it's going to be with the NO3. K has a +1 charge, NO3 has a 1- charge. So if I take those charges and switch them, I get KNO3, or essentially I need 1 K plus to balance out 1 NO3 minus. So that's the formula of one of my products. Okay, I'm going to do the same thing with my next product. Pb is taking the place of K, so Pb is now being combined with the Cl. If I look at Pb, it has more than one charge, but if I go to the other reactant, PbNO3 Pb has a 2+ charge, so I'm going to keep that charge. I want to keep the same charge, so it's Pb2+, and I have Cl-, and they switch and I get PbCl2. Make sure if any of these ionic formulas have subscripts of, let's say, 2 and 2, that you simplify. You always want an empirical or simplified formula for your ionic compounds. Also make sure that you've combined a positive and a negative ion, and that your positive ion is in front and your negative ion is in the back. Now these are my products. I don't care which one I put first, but they should both go on the product side on the right of the arrow. Right. Now I left space so that I can look up the solubility. If one of these things are soluble, they will be written as aqueous, AQ, and if something's insoluble, it will be a solid. So if I look up KNO3, K is always soluble, it's group 1, NO3 is always soluble, this is aqueous. If I look up PbCl2, this is insoluble, so I'll put an S. We also call this the precipitate, and that's why these are also called precipitation reactions. My last step would be to balance this. There's 2 Cl's on the right, so I need 2 in front of KCl, and then I need a 2 in front of KNO3 to balance both the K and the NO3. This is what's called a molecular equation. It's called that because we're writing all ionic compounds looking as if they stay together like as a molecule. If we want to write a net ionic equation, our next step would be to break up all soluble ionic compounds. Essentially, we're breaking up all things that are present entirely as ions in solution, and soluble ionic compounds are one thing that are present this way. So any ionic compound that you have written as AQ, you're going to break up. Okay, so I like to put check marks and X's to remind myself what I'm breaking up and what I'm leaving alone. So the first one's a soluble ionic, I'll break that up. So is the second. So is the first product, but the other product is a precipitate. It is not soluble. It will not be present as ions, so I'm going to put an X. You see solid, say stop. Okay, so everything I put a check mark, I'm going to break up into its ions. That means that those the constituent ions should be written with a charge. They're still aqueous, they're still in solution, and I also want to keep the same number of ions as I have already balanced. So for instance, the first one breaks up into Pb2+, and there's 2 nitrate ions. So any subscript that's not actually part of a polyatomic ion, I'm bringing in front, because it's no longer part of a formula, but I do have 2 nitrate ions in solution. Okay, the next one, I'm breaking up KCl. There's 2 K pluses and 2 Cl minuses. That coefficient of 2 is carried to everything after it. The next one, KNO3, breaks up into K plus and NO3 minus, but there's 2 of each because of the coefficient. And the last one, I'm going to keep exactly as is. I am not going to break it up, so I carry down any coefficient, any subscript, any phase exactly as is. This is what's called a complete ionic equation because you are completely breaking up every soluble ionic compound into its constituent ions. The next step to get to our net ionic equation is to look for any ion that's present on both the left and the right side of the equations. So in this reaction, for instance, 2K plus is on the left and it's also on the right of the reaction. So it's not really doing anything if it's there to start with and there to end with. So we call it a spectator ion. It's really just watching the show, so we can cancel it out. The same thing is true of NO3-. There's 2 NO3- on the left and 2 on the right. So we'll cancel those out. Make sure you do have the same number on each side. At this point you should, so if you end up having 1K plus and 2K plus, you should probably go back and check your work because there might be a slight error that you made. Okay, now I can rewrite what I have left, and that is my net ionic equation. So I'm left with Pb2 plus, 2Cl minus, creating the precipitate PbCl2. And that's essentially telling you what's happening. These two ions are coming out of solution to form a solid at the bottom of your reaction. Also make sure that at this point you can't simplify your coefficients anymore. A 1, a 2, and a 1 can't cancel out. After you eliminate spectator ions, a lot of times you can simplify. Let's look at one more example to try, and I'm going to go through this very quickly. You might want to pause and try this example first. So again, I'm going to take the 2 positive ions and switch places. Ca was with Cl, now it's taking the place where Li was, and it's going to be combined with PO4. Look up the charges. Ca is 2 plus, PO4 is 3 minus, switch them, and you get your new formula. You want to make sure your ionic compound has balanced charges. Remember that your subscripts might be changing. We'll take care of balancing later with coefficients. Okay, the Li was with PO4, now it's with Cl. These cancel out to give you LiCl. Make sure you have a positive and a negative ion combined. Make sure your positive ion is in front and your negative ion is behind it. We are now going to put these as our products. I left some space to put in phase and for balancing. If I look up calcium phosphate, it is insoluble, so I'll put a S for solid, and LiCl is soluble, so we'll put aqueous. Balance your reaction. I need 3 in front of CaCl2 to balance the calcium. I now have 6 chlorines on the left, so I need 6 chlorines on the right, and I need now 6 Lis on the left, so I'll put a 2 in front. Though it does not matter the order in which you balance, you should get the same answer. This is my molecular equation. Next, we should get the complete ionic equation, where we break up all soluble ionic compounds into ions. I will break up the first one because it is soluble. Same with the second. This first product is insoluble, so I will not break it up. And this last one is soluble, so I will break it up. So I'm breaking these up into ions. The first breaks up into 6 Li pluses and 2 PO4 3 minuses. Make sure that your ions have charges or it's incorrect. Make sure you carry down the correct numbers so that you carry your balancing back down. The next breaks up into 3 Ca2 pluses and 6 Cl minuses. Carry down your precipitate exactly as is. We are not breaking it up. And the last breaks up into 6 Li plus and 6 Cl minus. Let's cancel anything out that appears on both sides. Li plus appears on both sides. There's 6 and 6 of each. And the same thing happens with the Cl minus. We call those spectator ions. Let's carry down what we have left. Make sure we can't simplify. 2, 3, and 1 can't simplify. You might have done it where you have Ca2 plus in front and then PO4 3 minus. It doesn't matter what order you write your reactants or what order you write your products, as long as they are on the correct side of the reaction. And that's how you write a double replacement reaction and do the net ionic equation. If you get to acids and bases, you'll learn that you also break up strong acids and strong bases when doing a net ionic equation, and that can get a little bit more complicated because you have to memorize which are your strong acids and your strong bases.